Dear all, welcome all of you. So we'll start our session now. Today we are here to discuss some of the problems based on the course study guide in the organic retrosynthesis and problem solving approach. So we are gonna see some of the problems based on this course, and this course is taught by Professor Somik Nanda from the IIT Kharagpur. So as we have already discussed in the last video regarding the what topic that we are gonna see in this course, particularly the introductory remark that we have discussed already in the last video, and today we're gonna see some of the actual problems. So based on these topics, so I will just refresh some of the concepts from this one. So particularly, uh, so So the what is the target molecule? So basically, this is the molecule that we are gonna or we are planning to synthesize. So that's the target molecule. Second thing is the retrosynthetic analysis or retrosynthesis. So this is the process of mentally breaking down molecules into the starting materials or the commercially available, but more particularly the starting materials. The third important point is the retrosynthetic arrow. So this is basically shown by such representation. So used to indicate the reverse synthetic reactions. So we know the forward arrow, and so in the retrosynthesis we are using this. We are going to use this type of arrows to show the reverse synthetic reactions. Then the fourth important is the disconnection. So this is basically and the imaginary bond cleavage corresponding to the reverse of the real reaction. And there is a synthon and this synthetic equivalent. That term also we have already discussed, right? So basically, we will see some examples, and we are gonna discuss already. We are going to discuss some of these terms in the actual retrosynthetic analysis, some problems, right? So I will directly, without wasting time, directly move to the some of the natural products. So this type of natural products, let's say we can extract from the natural sources. And at the time when the organic synthesis was on the peak, that time there was the flow chart for this, like basically for some medicinally active ingredients. So they generally initially extracted from the plants or some biological source, and after extraction they were purified. Then the structure were characterized, and structure structures of these natural products were then characterized, and the fixed or the what you can say structures were identified. And then once the structure is identified, let's say example, such materials like here it is like the structure of menthol. It is obviously it's a natural products. So like this structure, once they identified, they were then look for the synthetic route for preparing such type of natural products. So this is the cis jasmine. So this is basically we all know the or this uh, it cis jasmine, and another is the quinine. So these are the natural products. So we'll see some examples. Similarly, this is the one of the natural products, and which term they which has the basically sorry, where is the just okay. We'll see the retrosynthesis of this natural product. So basically, this is, let's say this is our target molecule now. So what is this? This is a What is happening? Just let me just check once. It's all good, I think. It's in the area. Okay. Okay. So this is our target molecule. So target molecule. And if you do the retrosynthetic analysis for this one, so what you can see in this molecule, there are different parts present in this molecule. So I will first do the disconnection. Uh, so initially you can see here, so this bond can be cleaved. So these are just sort of imaginary disconnection that I am right now just showing. I will not directly solve the question, but I can show you here. So this is one part. This might be the one part. So what will be the cleaved part from this one? So this will be the O negative, and this can be comes from the phenol. Then if you look at here, after upon this bond cleavage, this center should be the electropositive. So this part should have attached any halogen or any sort of other groups upon disconnection. And further, if you look at here, so this part can also be cleaved from this position. Again, there is in this one, this is also one of the disconnection possible. And again, in this part here, there is possibility of another disconnection. And further, we can either disconnect here or again disconnect in the some other part. So what might be the fragments present in this? So this is the one fragment that we have identified, the central phenyl with the 2O negative, right? So this is one fragment. The another fragment is the uh, this CH2 double bond O. This might be the Cl or any let's say I will write only the synthon, the charge spaces here. So this is the delta, this is positive here, and again here also it should be the positive. The another part possible for this one is the from the uh, okay. So another part is NH2 and OMe, right? So this is another part, and in between, if you look at here, there is between these, sorry, after in between this in this portion, so we have already draw the phenoxide anion, so this is negatively charged. Then here it should be the CH2 positive and followed by, so this is the uh, this is the chiral center. We will draw that chiral center as it is. Further this CH2, and then there is a, sorry, here there is a bond breakage. So I will what I will do, I will write down here it as a positive charge, and followed by, in this position there should be the N CH2 CH3, sorry, here CH2 positive. So there should be in between, so these many and this NH, this should be the negative. So these are the some fragments are responsible are combined together to form this target molecule. And whatever this connection that I have shown all in the one step. But in actual, when you do the practical synthesis, we are not doing going to add or not possible to add all fragments in one step. So we have to move to stepwise manner. So we'll see some examples how the stepwise manner we can go. So let's say this is the one simple concept like simple reaction. So let's say I have such a similar molecule, and how I can do the disconnection of this molecule. So this is the in this case this is the target molecule. We'll break down every steps in the simple manner. So how this target molecule can we can achieve. So if we can do the disconnection here. So what we have now here the I'll draw intermediate step. This is pH CH2O. negative. This is the one synthon, and another part is this acyl cation. So this acyl cation is basically O, and the pH. So this will be the positive. So these two parts are formed upon disconnection, and this is the synthetic equivalent of pH CH2OH. So this is basically the the alcohol, and another part is, so this can be achieved from either chloride, or we can also do with the other possible, but we'll draw simple possible, let's say acyl chloride. So that's what given here. So this can be derived from the acyl chloride. So in this one, so what is the target molecule? So the target molecule is this part in the box. So this was our target molecule. So I will draw the short form. This is the target molecule. So this intermediate step, this CH2 O negative. So this is the synthon, and this is the synthetic equivalent of this synthon. Synthetic equivalent, right? So a similar case, this is the synthon, and this is synthetic equivalent, right? So this was the simple steps. We'll see some more simple reaction, and then go toward the some advanced problems. So let's say this is the second problem, and in this case, so this is the amylo halide molecule, and this is the name of this natural product. And if you look at in this molecule, so how we can achieve the synthesis of this molecule? So here you can see, here we can do the disconnection between these two bonds, this amide bond, right? Highlighted here in the, let's say I will just give the color coding. So this green will be the disconnection, right? So on this so we can do disconnection on this bond. So what do we get now? So this is the NO2 group will remain as it is. That's the NO2 comes from the target molecule, and here this acyl, this will be the positively charged, and this amide part, sorry, this nitrogen, this negative, the proton will be the same there, and this will be the phenyl ring. Right. So these two species we get from this uh, if you do the retrosynthesis of this target molecule, and how they can achieve from which molecules. So this positively charged, so this positively charged species can be from the pH C double bond O Cl, that is acyl chloride, right? So obviously it has the NO2 group, and the other species where it comes from, it can come from directly the NH2. So that's the simple NH2, and this just the phenyl with the methyl substituent, right? So we have break down this molecule into the two different starting materials, and simple as possible we have to do. So these are the, it seems they are the already commercially available, so we can stop our synthesis here, retrosynthesis analysis here, or also we can further move to simpler form, like so how this acyl chloride, let's say this acyl chloride is unstable, then we can achieve this acyl chloride from this pH C double bond O OH. And if you do the, so we know the one reaction, that is acid can be converted into the acyl chlorides by using, what are the reagent used for sorry here. So let's say we have the such acid. So I'm showing now here is the forward synthesis. So we have the acid. So this acid can be converted into the this acyl chloride. So this chloride by using SOCl2. If you add the SOCl2, and we need to add the, let's say, pyridine. So in that case, we can get the acyl chloride in this reaction. So this type of acyl chloride, let's say, so we need to take the substituted nitro substituted. If you take the nitrosubstituted acid, then we can get the nitrosubstituted acyl chloride in situ in the reaction. And within the reaction, if you just evaporate the SOCl2 and add the amine NH2. So this is pH. I will just draw the short form. If you add this amine, so we get our target molecule, right? So which has the NO2. So this is the forward synthesis that I have shown. And synthesis is basically reverse of the forward synthesis, right? So we can get this target molecule from this, and reagent required to add. So we don't really need any reagent because this reaction is quite straightforward. And if you just add the amine and here it is primary amine to the acyl chloride, it can directly gives the we get the amide. So this is the forward synthesis, and the backward synthesis or the reverse synthesis is this one. So this is how the retrosynthesis works, right? So this is simple example. Now let's say if we have the target molecule diaminozide. So this is the structure of diaminozide. So we don't really require to keep the names of this molecule. Uh, if you just forgot the name, that also okay. So let's say this is the target molecule and how this target molecule can be synthesized. So we'll do the retrosynthetic analysis. So what bond we can easily break. So this is the bond between the this amide bond we can cleave, right? So this bond is easy to cleave, and upon cleavage, what we got there is in between synthon. So what is the synthon? So OH. So this is the OH. That's the comes from acid. CH2, and sorry, here this will be the delta. Sorry, the positively charged, and the negatively charged species is this NMe. Right. So this is the negative charge species. Here there is a this this is the this should be the negatively charged, and then this can be derived from the obviously from the NH2, right? NMe, and this can be from the acyl chloride. Cl, right? So this is the retrosynthesis of this diaminoxide target diaminoxide molecule, right? So like this, we can do the retrosynthesis. So in these examples, what we have seen, the disconnection, how we can do the disconnection, what is the target molecule, what is the synthon, what is synthetic equivalent, right? So does anyone have any doubt in this? If you have doubt, you can just stop me in between. We'll discuss that one. Okay. So we have the next molecule, so which is very common. So I believe everyone had at some point have taken the paracetamol. So this is the structure of paracetamol, a simple molecule, and which is obviously the antipyretic, I think, right? Drug, and commercially as well as the widely used, right? This is the paracetamol. So if I just draw, it is so this is how generally shown everywhere. N double bond O, and this is OH. So this is how we generally observe the structure. If you just Google it also, so we can see the structure in this manner. I just draw it's vertical. That's okay, right? So this is the paracetamol, and this molecule is our target molecule now. TM. I will just draw the short form. This is the target molecule, and how this molecule can be it's synthesized. So if I just do the retrosynthetic analysis, So which bond we can cleave? Can anyone tell me? So if we look at closely in this molecule, so this is the bond, obviously, that we can cleave. And if we look at the synthons we get upon cleavage, so this will be the negatively charged. And what we get here? We get the Cl. And this can be either acyl chloride or acetic anhydride because both give the why this or sometime it is possible that we can achieve that type of species or the synthon from more than two, one or more uh, possible starting materials. So this acyl source that can come from the either acyl chloride or can be from the acetic anhydride, and both are commercially available. So whichever we have available in our lab that we generally use for the to perform such type of reactions, right? So this is the fourth target molecule that I have shown, right? Then if you look at the another molecule, so in this molecule, so can anyone tell where the disconnection can goes? So if you look at closely this molecule, what you can observe? So this is the one part, and this is the another part in the molecule. There are two parts, simple, right? And now where is the where possibility for the bond breaking? So this bond is more susceptible for the or more practically toward the disconnection. So what can be two species from we get upon disconnection, we get the this S negative, and this S negative along with the what we get another part, this is the CH2. This can be the positive now because if you look at the bond polarity, so the sulfur is more electronegative compared to the carbon, and therefore so this should be the bond cleavage should be like this, with the sulfur got the negative charge and the CH2 group got the positive charge. And this can be comes from either bromo or iodo starting metal, right? CH2, and this phenyl ring, I'll just draw the, okay, just ignore the handwriting. And another part can be comes from, so this part can be come from the SH, right? So if you just add this pH SH in terms of the base to the this bromo CH2 pH, so what it will give? It will give the pH S CH2 pH, right? So this is what the retrosynthesis and the forward synthesis of this target molecule. Any doubt in this one? Okay, I will take some more example now, similar manner. So let's say this is the catabine ethyl ester, and if you want to do the retrosynthesis, I have shown the already where we can do the retrosynthesis. So you can directly. So this is the possible retrosynthesis possible on this bond. So we have the R CH2, and I will directly right now I will directly start uh, directly instead of synthon, I will directly write down the synthetic equivalent of that species. So what can be the starting materials for this one? So this can be either bromo. I will just for simplicity I will just draw the bromo, and this can be the NH2. This one. OET. So these are the two starting materials for this citabine is ethyl ester molecule. Then right. So then we'll move to the one of the intermediate for the molecule that I have shown very initially of this our today's session. So if you look at this molecule, and in this molecule I have shown multiple disconnection options. So let's say if you do the disconnection on the D point. So upon this, just a second. So okay, so in this molecule, so if you do the disconnection on the A point, so well, sorry, here it is. Okay, if you do the disconnection, I'll just select the some different color, so it is easy to understand. Okay, I'll take this one. So if you do the disconnection on this A point, so here, so if you do the disconnection here, so what will happen? So upon disconnection here, so this part will be. So if you do the disconnection on this A point, so what species we can get from this one? So we get, so this entire part comes from the OH. So this is the OH and this will be the uh, PHCH2 positive. Obviously, it can come from the PHCH2Br, right? BrCH2PH. Second possibility is he disconnection on this point. So upon disconnection on this point, the point B, so what we get? So this entire part with this alcohol, and at this point there will be this cation. So this cation, and then that part cation can comes from the either bromo compound. Whenever I am writing bromo, it can be iodo also. That also be okay, or else I will just draw the good living group. Any that can be also the tosylate also. So this X and this X can equal to the either bromo or iodo or also good living group, basically OTS or any similar group, similar good living group, right? Like this. The same case with the earlier that example I shown here. Then if you do the disconnection on this point, let's say the C, what we get the what species we can get. So this can be PHCH2 NH2, and further this remaining part either can come from this bromo version or maybe iodo or any good living group in place of the in place of this bromo. And further next disconnection possible on this D point. So upon disconnection on this D point, so I'll just remove other. So this point, so we can get this PH CH2 cation followed by here this entire part. So for one simple molecule, there are several possibility of the disconnections are available and depends upon. So okay, we'll move check now. So what you will do when you have similar options available, right? So I'll just take this molecule now, and instead of this, I will So forget about this other disconnection. So if you want to do the forward synthesis now, so what you can choose from this one. So how you will start your synthesis. So if you want to synthesize this target molecule, and so forget about the whatever the disconnection they have shown. So what will be your retrosynthesis, or what will be your forward synthesis for this molecule? So what I do in such case, if I have such a similar sort of synthesis target molecule, I will identify the simple possible reaction first. So let's say this part seems symmetrical and which has this PHCH2 group. I will do that reaction first. We have identified the how the rate of synthesis is possible. Now, if you want to move to the actual synthesis or the forward synthesis, what one can do. So just start with this molecule. Then do the first reaction. Let's say pH CH2 Br. So what we'll get in this reaction? We get this will be the OH, sorry, the O, CH2, pH. So just you need to add the base in the reaction. So this reaction will works. What will be the next reaction, next step in this one? So the next step will be, sorry, here there is OH, right? Next step focus on protecting this another part, or one can do the prepare the other part first and then do the couple that part with this intermediate. So I will give the labeling also. So this is the first, this is the second intermediate. Sorry, this one and two are starting material. This is the intermediate now, three, right? And other part is what other parts available here? I'll just take the different color. So if you look at this part, that part can be synthesized independently. So let's say we can take the PHCH2 Br plus what we can take. So we can select this part, right? So this available part. So what I can do, I NH2 CH2 Br. So if you have in our reaction like this one, but we have to take into consideration. So this molecule have this bromo, and this molecule also have this bromo. So this NH2 can also attack on its own bromo CBr bond, right? So instead of bromo, if you take the good leaving group compared to this bromo, we can get the selectively the coupling of this NH2 selectively this PHCH2 X. So this should be the good leaving group compared to this bromo of this part, right? So if you have the good leaving group, let's say tosylate, in that case, this power problem will not be there. Then we get the pH CH2 NH2, obviously the CH2 CH2 Br, that part, remaining part, right? And once we get this, so this will be the starting material 4, starting material 5, and this is now intermediate 6, right? So this intermediate 6, if you couple just intermediate 6 with the intermediate 3, you can clearly see this is the hydroxy group and this is the bromo, alkyl bromide. So we can couple these two groups, and upon coupling, we get our target molecule, right? So like this, initially what we have analyzed from this molecule, we have analyzed different disconnection pathways, and we analyzed what are the possible starting materials. And from that, now when we started our synthesis, for us, it was easy to do the forward synthesis because we already did the analysis initially. So right now, if I want to have synthesize this target molecule, I will proceed like in this manner. So I will synthesize this. I will couple this one and two using the base as a catalyst. to get this intermediate 3. And further also parallelly, what I will do, I will couple this starting material 4 with the starting material 5. These are the simple starting material, and I believe they are commercial. So upon coupling with the starting material 4 and 5, we can get this intermediate 6 and this intermediate 6, right? And once we have the intermediate 6 and intermediate 3 in hand, this can be coupled to get our target molecule. So this base catalyzed reaction gives the our target molecule again, right? So this is what it is possible with this simple doing retrosynthesis of this simple molecule. Does anyone have any doubt here? Okay, if you don't have any doubt in the previous question, so in this question, I will take the another question. Just analyze this slide, and we'll solve this question in 5 minutes. Okay, if you have analyzed this slide, so you might have noticed some lapses in the previous forward synthesis. What was the lapse? So in this first step that we have shown, what was the drawback here in this step? So if you directly couple this one, we have to add selectively one equivalent of this PHCH2Br. Otherwise, what will happen? So this another free hydroxy group can also coupled with this another PHCH2Br part, and we get the dicouple products. So that will be a side product in this step. So in this case, we need to add only one equivalent of this starting material. Although if you have one equivalent, but still there in the reaction, there will we get the some side product with this dicoupled. The another hydroxy can also be the coupled with this PHCH2, and we get the side product, major side products. But in that case, what we can do? So here the benzyl chloride protection. So this benzyl chloride protection, and again someone may ask why this benzyl chloride protection. This can also goes to another hydroxy group as well. But if you look at the reaction condition for this benzyl chloride protection, uh, this the condition is mild generally because this benzyl chloride is the much reactive group. So if you add selectively one equivalent without any heating, this reaction works. So therefore, this benzene protection were used. Then if you have this dibromo compound, so this is another route, right? Possible route. If you add this dibromo, so this hydroxy coupled with the this bromo part, and we get this new bond formation. Then if you add the benzene BnNH2, so that will be the get substituted here, and upon the reduction with the catalyst, palladium catalyst, obviously, we get the this is basically the deprotection step. So we can deprotect this Bn part, and we get the free hydroxy group. And once you get the free hydroxy, so if you just look at the other part, remaining part, this is the acetyl chloride fluorosubstituted alpha chloroacetyl chloride. This coupled with these NH2 CH2 CH2 OMe. This NH2 will replace this chlorine from the amide. So this is the amide form. And once this benzene NH2 and this alpha uh, chloroamide part. So this alpha chloroamide, right? So this is the chloro, this is the amide group. So this alpha chloroamide. So they can couple in place of base. So this entire part is now get adds with this free hydroxy group, right? So this is just referred as a R1, and this entire part will be the this remaining part as a R2. So this is the remaining part, right? So this is what we get in this reaction. And further, if we add this epoxide, so this epoxide in place of base, so this hydrogen of this NH, so with this pH, right? So I will just elaborate the structure just for understanding. So this is the part with the pH CH2. So this is the that part with the CH2O directing upward. So that part remain come from this epoxide, right? And this is the CH2 groups, which is comes from the epoxide CH2 of this epoxide, and the nitrogen. This nitrogen is now here, and this remaining part will be there. And further, last step is the catalytic reduction of these benzene. So earlier also we have seen this benzene deprotection, so that is done here from this nitrogen to get the target molecule. So this is the forward synthesis of this ICI D7114 molecule, which I have shown very initially. This one. Right now, for you, it will be difficult to understand directly such big molecules, but we just have to keep in mind. So this is what at the end of the course we are able to solve such big problems. Now I will take some simple problems. So okay, so we have one starting material, sorry, one target molecule, and we'll see how we can able to do the synthesis on that molecule. So this is the molecule, target molecule, and just try to do the disconnection on this molecule. So if you analyze closely this molecule, the similar bond you can also observe in this molecule as well. So what are the more susceptible bond for the disconnection? So if you look closely, so here we can do the disconnection. So this will be the A disconnection. Also we can do the disconnection here. So this will be the B. And what we can get the starting material, we get this NH2. Right now I will not draw the charge species. I will directly draw the possible starting material. So this can be the NH2. The middle part, before going to middle part, I will draw the two terminal part first. Here it can be hydroxy. And the middle part, if you look closely at this middle part, so what it have? It has CH2. This CH2 has the O, and here there is another CH2, right? So if you look closely, so this can be derived from, as we have seen in one example earlier, the epoxide one. So this can be derived from such compound, right? That's the epoxide. So I'll just draw the clear structure of this epoxide. So this can be from this epoxide, and here it can be either bromo or any good living group, right? So this X can be bromo or iodo or tosylate. Okay, so these are the three possible uh, three starting materials required to get our target molecule, right? And if you do the forward synthesis, that also the part of retrosynthesis you have to keep in mind. Otherwise, you just do the disconnection, and the ultimate purpose is for the forward synthesis. So that's why we are learning this retrosynthesis, right? So if you want to synthesize this molecule, so what I will start, where you go will start your reaction. So I will start the reaction with this alcohol. I will take this epoxide molecule, epoxide part. So this epoxide part will be, and the CH2 Br, and in presence of acid H3O plus, what will happen? So this species epoxide will be protonated, and this can become good living group now. So, and if you add this alcohol, so this can be now attack on this part, and this part gets open. Why on these parts only? Mainly because this cleavage occur in the SN2 fashion, and the attack on the secondary position is sterically hindered. So major attack will be takes place on the this primary center, right? And what we will get in this step, we get now the our first intermediate, so which is this naphthyl with the OH here, which has the now this CH2 from the epoxide. This is CH. Now this become OH, and this will be the CH2 Br. And if you add this NH2 part on this one, so I will take it on the next slide. Okay, so if you just take the other part, that is the, what was the other part? NH2, sorry, this CH3 and this. NH2. So if you add this part in place of the base, what will happen? The nucleophile substitution reaction occurs, right? So this nucleophile attack here, this bromo get eliminated, and we get our target molecule. Does anyone have any doubt in this question? Sorry, in this our retrosynthesis uh, problem? This is the CH2. Now it has the N with this two methyl group and H. This was our target molecule, right? And we are able to synthesize that target molecule. So we are slowly moving to the from the target molecule to different disconnection, and also some we also need to solve some functional group insertion, or what it called FGI, right? Functional group interconversion. And for that, we'll see some uh, more problems on the now on the uh, functional group uh, inversion. Sorry, interchange or inversion. Functional group interconversion. So basically, in this functional group interconversion, one functional group we can change to another functional group to carry out or for simplicity of our reaction. And some examples we'll see here. So we'll see an example of the some natural products more to understand this functional group interconversion now, because we already covered the disconnection now. So let's say this is the one of the forward synthesis. So in this case, this is the target molecule, and the synthesis, forward synthesis, I will show here. So this is the forward synthesis. So they start with the starting material one. So this coupled with the so the starting material and the starting material two form the imine. So if you have the imine and the keto group, sorry, amine and the keto group, it forms the imine. So this is basically do the imine formation, right? And then if you do the reduction of this imine, so what will happen? We get amine. So the first step, the imine formation. The second step is now the reduction of this imine to amine. And now if you look at here, so if you add this second target molecule, sorry, this was the first starting material. So the second starting material one. This is SM2. This is the intermediate one. Now this is the intermediate two. This is the starting material three. So I will use the terminology. So you will get habit of using this terminology. This is the starting material three, right? because these are the intermediates because that we have synthesized. So therefore we are calling it as a intermediates. So this intermediate two, when you couple with the starting material three, which is the acyl chloride, so what will happen? So this NH2 now attack on this, the lone pair on the nitrogen attack on this part, and the chlorine get eliminated. So this one attack on the carbonyl center and the chlorine get eliminated. So we get our starting material. So that's the ophenylene molecule. So this is the forward synthesis of this ophenylene molecule. And so where if you want to analyze where the disconnection and all occur in this final molecule, so this was come from the one part, this from the another part. So there was three different starting materials involved, and we did the stepwise synthesis as we can see, as we have already discussed this one, the amine formation followed by the reduction, and then the so basically this we did the in this case the reduction of this one, basically functional group interconversion. That step we have did here. Now we'll see some more example on this FGI, functional group interconversion. Okay, so this is the retrosynthetic analysis of this fenfluramine, which is a natural product again. And if you look at these molecule, so where the FGI possible here? So if you look at here on this part, this was the CH2, and upon functional group interconversion, this will be the amide. So basically, this CH2 part is now the amide keto part, right? So that's basically the FGI. So one functional group is converted into the another functional group. So this can comes from. So basically, why we have written like this? So this can be, that's what we are proposing. This can be come from this keto part, this CH2 group. So that's basically the functional group interconversion, and this is basically upon reduction of this molecule, we can get in the forward manner this final molecule, and which reduction step that we will see in the when we are doing the forward synthesis. And what will okay, so the first step was functional group interconversion. Now if you look at here, so this is basically can come from the this part is NH2, and this can come from the acyl chloride, right? So we did the disconnection here. So this is the amide bond. So we did the cleavage of the CN bond, and this is the DIS disconnection. Now here, if you look at this amine, this is the one part, and obviously the acyl chloride that will be the another. Now if you look at this amine and this entire molecule, from where we can synthesize this amine? So we can synthesize this amine from this keto group, right? So how that will be reduction and how this amine. So we already one example seen this. If you have the keto, we can do the imine of that keto, imine, right? And the imine upon reduction can be converted into the amine, right? So like this manner, This is the forward synthesis is possible. Keto can convert into the imine, and imine we can reduce to the amine. So that's what we have shown here. So if you look at the this is the retrosynthetic analysis of this fenfluramine, and if you look at the forward synthesis of this same molecule, so what will be the forward synthesis? I will directly show the forward synthesis. So this is the forward synthesis. So basically, it started with this starting keto. This is the starting material, and upon reduction of the sorry, if you treated this keto compound with the NH2H, so it will form the imine, right? And this sorry, the oxime, because it has the OH group, so we can't call it as a imine. It will be the oxime. So upon reduction of this oxime, we get the amine. So once we get the amine, what we can do, we can add the acetyl chloride on this amine. So what we will get, this pH I will draw directly, pH with the CF3. Then we have the CH2, N, H. So this will be CH3 like this, CH3, right? So this is what, and again, so this amide we can reduce to the normal uh, I will just, highlight the part. So this is the amide, right? And this part we can reduce to the CH2 by using LiAlH4. What will be? Should be N. This will be now CH2 and CH3. Further, this other part will be the remain as it is. So I'll draw the full structure in the target molecule. This will be CF3. Right. So this is what our target molecule was. Right. So this is the forward synthesis of this fenfluramine molecule. Does anyone have any doubt in this one? Again, I will show you one more example for this functional group interconversion. So let's say I have the same example that I will show this one, and any let's say R2 or anything. Here there is R1, here there is R3. So what will be this come from? This will be, we'll draw FGI. This can be comes from R1, this R3, and this will be NR2. This can come from the imine, right? This amine can come from, and this imine can come from, again, functional group interconversion. This can be from this keto. So have you understand this concept of functional group interconversion? FGI. This is we're gonna use in later part when we are going to for retrosynthesis of some other molecules. You may found some problems. They are different from the whatever the taught by professor, but the concepts are similar. And this retrosynthesis is more widely used in the actual research when you uh, when you want to synthesize some molecules, then this part will be very useful. And this is basically the more practical than the theoretical. So we have to look at the practical aspects of these, whether this reaction possible practically or not, instead of only theoretical understanding. So when you are doing actual retrosynthesis in lab, so if you want to synthesize some target molecule, then we have to look at the feasibility of the reactions as well. And that part will be more will be when you go into the research, so that you will encounter some such problems. But for simplicity, I will just explain one of the uh, uh, s- example that you can see. So let's say if I have, oh, sorry, OCH3, and here also there is some, let's say, right. So this is the nitrogen, right? So like this molecule, and we want to so what you can see simply, retrosynthesis of this molecule, you can do the disconnection on this point. So what you can get the two simple starting material. This is just a hypothetical example that I am showing. So this can be CH3 and it can be N. This can be the basically a carbazole, right? So these two starting material you can get ideally in this case. And again, if you do the simple further reductions of this molecule, this can be comes from simple OCH3 molecule. But when you try out to do the some reaction in this manner, so what happened? So this CN bond formation. So this carbazole plus iodo or this one, this is not much that easy step. So, so this is one. These are the two starting material you have now. And if you try to perform the reaction, so there are several possible conditions possible. So let's say the first condition is, uh, obviously you need to take here some X group. So we need to look at the what X can be possible. So for this reaction, this X can be either bromo, iodo, or also we can use the, let's say, the fluoro. So these are some possible, and if you have some, so basically take simple, for simplicity, just take these three, and the reaction conditions can be now vary depends upon the availability of the chemicals also on the substrates. So let's say if you have the bromo, then what type of reaction that we can able to perform on this bromo? So we can use the Buchwald coupling. So the Buchwald coupling basically the palladium catalyzed. So if you just search Google it, so you can observe palladium dibenzylidine acetone DBA thrice. So this catalyst, we need to add the base and the solvent. Also, we need to add the uh, ligands, basically the XPOS or XenPOS, this type of some advanced reagent used for this promo. But this can be the very simple if you have used the fluoro instead of bromo. So if you use the fluoro, that time what will happen? You perform the reaction only using just add the base. That's it. Based in DMF solvent. So if you have the fluoro on the place of here X, so the reaction will be only if you have only the base and this carbazole, this reaction will works directly and we get the our product. But if you have the iodo, then the reaction condition will be different. We need to use the copper iodide, the 110 phenanthroline, then the base, either K2CO3 or cesium carbonate. So like this base we need to use, and again the solvent at higher temperature. So this for this, obviously in all cases the reaction temperature generally more than 150 required. But if you look at the simplicity of these reactions, so if you have the fluoro, the reaction is very simple. But if you don't have the fluoro version available, and if you have the bromo version available, we need to do reaction in this reagent combination like palladium dba thrice base. We need to use the strong base. Further, we need to use the ligands uh, as well in this reaction. And again, if you have the iodo, the reaction condition again will be the different. So depending upon the reagent that available with us, we need to select the reagent combination. Right. I hope you understand the aspects at least in this example. So depends upon our availability of reagent also, or also the simplicity of the reaction. We have to select our reaction path. So I hope you understand some part of this topic. So, if you have any doubt, please ask me, or we'll stop here for today and we'll be back on the next Tuesday again. So, any doubt here? You can put it to the chat box. Please wait. I think I will add the link for the the drive. So, which has the several reference book. You can download from that one. So that will be helpful for you in future. Just keep downloading reference books. There are a lot of reference books I have. So I will share that link with you in the chat box. Okay. And also, if anyone have, so can you check whether this books you can able to view or not? So this is the link for the OneDrive in which I think what are the books available here. So there will be a J. Jack Lee name reaction book, also a guide to the mechanism. Then there will be a Carruthers, Bruce, again Pinar, Jerry Marsh, also there, McMurray, Organic Chemistry, 8th edition also there. Then Modern Organic Chemistry by Erich, also there. Morrison Boyd, name reaction by J. Jack Lee, I think, Lee. Then there is also PDF of the nuns, and I think there is again the Claydon and other. Yeah, there are several. So, and I have kept this open access so anyone can download. So, okay, we'll back to our course. So you can refer that reference books to solve some problems. So if you enjoy the today's session, then thank you for joining, and we'll see you on the next Tuesday. So I have added all the reference books in that one. So feel free to share with your friends also that books. So, and if you have any books PDF other than that one, you can share with me. I will add into that one drive. So it will help to other also. All right. So thank you so much for joining and see you on next Tuesday.